Okay, welcome. This will wrap it up in our series on trig identities. Hopefully you've memorized all 23 of those trig identities. If not, you got some work to do there. And then the part 3 screencast showing you examples where fractions are involved. That's a pretty big deal. Seeing how to work your way through these simplified questions can be tough. So practice those and the homework ones as well. This screencast will center on when factoring is involved. Like, why wouldn't we try factoring? Well, of course, and where does this fit in the context of your life in algebra? As I've mentioned in our course, pre-calculus is a summative assessment of all the algebra that you've studied all the way up through the last 5 years, I guess. And so this usually stands as the most challenging, but just so abstract. There's no numbers really anywhere except for that number 1 right there. And then, for that, it's a summative assessment of all the algebra because folks see calculus as really the next step. You need to be a master of all things algebra when you go into calculus. A lot of the calculus, no calculator questions involve quite a bit of rigorous algebra manipulation, and so you need to be able to spot things like factoring, common denominators, and all that other stuff. And then actually replacing expressions is also a big deal. So that's my sales pitch. If you are not entering calculus, then you are still doing a summative assessment of all of your algebra. That's where it fits into pre-calculus. Okay, so factoring. Example 3a says factor secant squared minus 1. Just a reminder that when you see this notation like this, it is noting at you that it is secant theta times secant theta. A deep dive back, secant theta, we would put some input in there and we would secant that and it would turn into a number, and then we would multiply that by itself. The notation, as I said, in the trig expression is a little bit of getting used to because the 2 kind of fits in over there for reasons that I already mentioned in another screencast. That's why we do it like that. You will see a lot of cos squared theta minus 1, sine squared theta minus 1, 1 minus cos squared theta, or 1 minus sine squared theta, or 1 minus tan squared theta. And in each of those cases, you need to be able to factor using difference of squares. The factoring of difference of squares follows a very straightforward and easy to follow pattern. It is, and even more so with these trig ones, because the number 1 is involved so much, you're going to have a plus or a minus 1, and you're going to have if you want to call it, the square root of secant squared theta. It's just a secant theta times a secant theta. That's it. That's one that you have finished, I would think. And then we'll move on to our second type of factoring. So this is reviewing all the factoring, and this might be a couple of years since you really got into this. We've got factoring with the AC method, but now in the context of trig coming at you right here. Example 3b is factor 4 tan squared theta plus, I've put a 1 tan theta minus 3. Pause and come back with the correct answer. Let's go with the correct answer. Hint, you're going to use the AC method. Okay. We have most of the solution there. It is perfect coming up there. I did a replacement, and actually I like to fit this into the pre-calc course again for the folks going up to calc. It's getting to the point where it's nice to replace out some things and then do the algebra without the tan thetas in there, as you're going to see up in the calculus course as well. And then for those folks, again, not going to calc, this is a summative assessment of your factoring skills, and again, for you all too, I think it's good to replace. Once you've done about 10 or 30 of these, then you'll get the hang of them, and maybe you'll just leave the tans in there. But in order to proceed through the AC method, I would prefer to have just x's. So this should be the last time I explain to pre-calculus students what the AC method is. Given a trinomial, a quadratic trinomial, we have an a and a c, and that's the first coefficient in the front with the x squareds, and it's this -3 in this case, the constant so-called c term. If a trinomial can be factored, then there must be some combination of numbers whose product is ac and whose sum is the b value, b being in the middle. In this case, the b value is 1, and I don't know why that 1 disappeared all of a sudden. There it is again. We've got to find that number combination if this factors. And it turns out there are 2 numbers whose product is -12 and whose sum is 1, and that combination of numbers is -3 and 4. In order to perform the AC method, you also need to be in understanding of the fact that middle term b can be split apart, sometimes called the splitting method, splitting the middle term into the sum. That's the sum. That's the whole point about that sum. Into the negative 3x and the positive 4x that you see there. It does not matter what order you put those into, but it does matter that you keep their signs correct. After that, you have what would be known as a quadrinomial, I guess, a four-nomial, where there are four terms, and four-termers can be factored by grouping, and that's what I've done here. There is a common factor of x in each of those, and that's what I've put out the front to leave 4x minus 3. Then I take a look at my second pair here, and it is actually indeed 4x minus 3. So you go, whoa, that's amazing. But you also have to have a placeholder plus 1 here, because remember, this is multiplication that's happening. Okay, that is just about done, the AC method. What is going to happen now is you've got 4x minus 3, that's one of the factors, and then x plus 1 is the other factor. Now, we weren't asked to factor with x's, we were asked to factor with tangent thetas. And so that's what we need to put into our answer. And that is, there's the 4 tan theta plus 1 and 4 tan theta minus 3. That's actually the factored form. Why would anybody do that? Well, if you were up against a trig equation, if this was actually set up equal to a number, like let's say 0, then now you would have two separate expressions, two more straightforward, they're not easy, but better equations to solve set up equal to 0. Anyway, that is factoring a trinomial with trigonometry involved, okay? The next problem is of the same type. Let me set that up, and then I'll come back and show you how to do it. This one says factor cosecant squared x minus cotan x minus 3. Okay, what's the problem here? Yeah, we don't have the same function. That's a problem, and you're going to need to replace in some fashion so that you can get the same function in here. That throws people off a little bit because you see that there are x's and you feel like we really should be able to just do this, I guess, like Nike or something. No, you have to have an agreement of the function as well. Now, I've given a hint here. Cosecant squared x, in case you forgot or haven't memorized it yet, is actually equal to 1 plus cotan squared x. So go ahead and do the replacing. I've set that up and I've given you the hint here. You're going to factor. Maybe you'll need AC method. Maybe you'll see it a little bit more quickly. Maybe you'll replace out the expressions. Maybe you won't. Give it a try. Come back, see how you did. Okay, and the answer reappears. There it is. What did I do? I replaced 1 plus cotan squared x. That was this guy here. Let's put a blue around that because then everybody will know it. That was the replace. Okay, and then there is a 1 out here that can be combined with a negative 3 to get the negative 2 at the end. I've just gone ahead in one step and organized it into the familiar squareds, linears, and constants. The so-called ax squared plus bx plus c that leads you to factoring it into cotan x minus 2 and cotan x plus 1. How did that happen? Well, the AC in this case, because there was a 1 in the front, the AC is just negative 2, so 1 and negative 2. I'm looking for two numbers whose product is negative 2 and whose sum is negative 1, because there's a b value of negative 1. Not a whole lot of factors, not a lot of combinations of negative 2, so it was negative 2 and positive 1. And since we have a 1 in the front of this trinomial, it doesn't make any difference which order you put it. Notice in one like this, again, with a 1 coefficient with the squared term, you might have remembered these as the kind of the easy kind. In fact, a lot of you guys call it the AC method in a case like the one we just did. And I don't know what you call this one, but it's still the AC method of factoring. It's just when the 1 is in the front, you don't have to do all that splitting the middle term, as you may or may not have ever been told by your math teacher. You can still do the splitting in this case, and it just simplifies down to what you see. So usually the teacher doesn't show you. Anyway, I'm rambling on. Let's get to probably our last example, and it's a real doozy. So if you feel like you're feeling uncomfortable or something like that, you may want to go get a drink of water, stretch your legs, and come back for example 9. Example 9 brings together logarithm, natural log, as you see there, and, well, absolute value. I'll talk about that just briefly. That's not actually, I mean, it's important, but it's not something to throw you off. And then cosecant's in there and tangent is in there. It says to rewrite that as a single logarithm. Okay, Let's take it from the top. This is not something that you should expect on Just Arts summative that we're having right now. Potential final exam question because it brings together a few different ideas. But yeah, other than that, this is just a good little review of one natural log property and then a whole bunch of simplifying with trig identities. First and foremost, the property of logs that you should recall is if I'm adding together natural log expressions, then I can perform multiplication, right? So you've got cosecant theta and tan theta that can be put together. Just quick word on the absolute values. The reason why absolute value is put in here is because, as you remember, natural log has a domain restriction. Natural log can only be performed on positives, actually. Even 0 wouldn't work, but that's what we are getting into here. That's why we put absolute value around that, okay, just to make it mathematically legit. And we'll just keep it there the whole time. But yeah, no need to dwell on that one, and I don't need to take any questions about that. That's more of a formality. Okay, so gotta multiply some stuff together, and then you're gonna simplify. Do the best you can, and come back to see how you did. Okay, hopefully you got the natural log of the absolute value of the secant of theta for your answer. If you didn't, let me walk you through it. Just as a I don't know, sort of a throwback here. As you may know, I teach the advanced geo, and we've done lots of proving and stuff. Hopefully this throws you back to geo when you made a statement and you had a reason. Another statement, another reason, another statement, another reason, and then finally a statement and a reason. The first was the property of logarithms that we saw. It was called the product property, I guess, if you want to call it like that, of logarithms, that says I can take the thing that's being logarithmed and multiply by the other thing that's being logarithmed, as long as you have the same base in your logarithm and you're doing addition. So I got that far. And then I need to replace, because cosecant theta, tan theta is obviously not as simple as we can get, because we know now we have 23 identities memorized in the back of our mind. We know we can get this more simple. And that's the goal, right? You don't want to evaluate a cosecant theta and a tan theta if you could do better than that. It does take a sideways step, though, for sure. I can agree. It doesn't look like we're getting any closer to simple when we replace out with our reciprocal identity of cosecant with 1 over sine, and that we have tan as sine theta over cos theta. It doesn't seem more simple, but woohoo, we have sines in the denominator and in the numerator, and so that expression can be simplified. We knew it. Gets down to 1 over cos sine theta. Once again, all contained within a logarithm, natural log, within an absolute value. Again, comment on the absolute value. It has to be there because the value of this on the inside could turn into a negative, and we can't have that happen. Questions have to be asked also about the fact that it would be 0 at some points. 1 over cos theta, secant theta. Actually, maybe the value of secant theta never turns into 0. Anyway, I'll ponder that. Off to the side by myself. And if you have questions about that piece alone, don't worry too much about it. It's not relevant for our course. We would never test you on anything like that. It's more for us to ponder on the outsides. Anyway, that is it for our series of videos about trig identities. We got you this far. Tough week maybe to digest all this content, but there it is. And not that many practice problems, to be honest. There are 4, 8, 11, and 12, 13, 14, 15, 16, 17 practice problems. Don't forget the Jamboard problems. The ones that are contained in these videos are also excellent ones to do. I can't remember off the top of my head how many I've covered here. Let's say about 10 or so. And, that should be enough. That plus a whole bunch of memorizing of these identities. You got to have those identities memorized, or it's just not going to come to you when you sit down and look at an expression like we've covered in these videos. Okay? Anyway, thanks very much.